All right, welcome to Evening with Chemistry and Mrs. Flint. Thank you. Thank you very much. All right, you can stop. All right, we've been doing stoichiometry, and I really do feel that this is a great way of looking at this. So I'm going to just do this note sheet for what we did in class in case you were absent. So we have reactants and we've got products, and then you've got your arrow that goes in the middle. So on the left side you have reactants, and on the right side you have products. This particular worksheet is saying that this is a given. We've been calling this the known. So you're given a known, and let's say that the known you're given is in the unit of grams. Well, in order to do this problem, we're going to have to convert to the molar mass. So anything with a double-lined box is going to be a conversion factor. We're going to get the molar mass by looking up the mass of each element, and that's going to give you the weight of 1 mole. Remember, the G for grams stands for grab your periodic table, because you're going to have to calculate that. So when you've finished with the molar mass step, you'll have converted your reactant, or your known, to moles. From moles, we're trying to switch from the reactant side to the product side, or to maybe even another reactant. So basically what we're switching to is going from our known to our unknown. And this is going to be the bridge that takes us from the one reactant, or that is our known, to the product, or whatever is unknown. So once we've done this step, we've now going to have the moles of the unknown. If we need our answer in grams, we're going to have another conversion factor. That's going to be the grams of our unknown, which will give us 1 mole. So you're going to have to grab your periodic table again. And you'll end up with what you want, which is your unknown. So when we're looking at this, we've got 2 sides of the problem. We've got one side of the problem that is the known. We've got the other side of the problem that is the unknown. To look at it in a different way, here we've got a reaction. So in this reaction, A is going to be our known. B is going to be our unknown. This would be the coefficient for the known, and this would be the coefficient for the unknown. So we're going to put a box around those, because those are going to be our bridge. The bridge that's going to go from our known to our unknown. So that's our bridge. So a problem, if you're starting with grams, you're given grams of A, you're going to need to calculate the molar mass. So that's going to be the weight of 1 mole of our known. So this is going to be the known. This is going to be labeled as the known. Now we have our mole ratio bridge. We've got our known, and we're going to have our unknown on the top. To finish this problem, you're going to need to have the molar mass again, which means grab your periodic table, and this time you're going to be calculating the molar mass of the unknown. And you'll have 1 mole of the unknown is this many grams. So you're calculating the molar mass in grams is going on the top. And when you're finished, that's going to give you the unknown number of grams. So again, looking at this problem, you can see that we've got it divided into a known side and an unknown side. And the bridge is what connects these two things together. So let's go ahead and look at a couple problems. It says sodium metal burns in air according to the balanced reaction shown below. You can see that this is already balanced because it has coefficients. And of course, with coefficients, if it's not written, that just tells you that you've got 1. So this would say 4 moles of Na plus 1 mole of O2 gas will yield 2 moles of Na2O. It says complete the setups with the correct factors to answer the following questions. So, how many moles of oxygen are needed to completely react with 9.5 grams of sodium? So there's my known. And I'm going to go up to my equation and I'm going to box that because that's the coefficient that I need for my known. Now I'm going to identify my unknown. How many moles of oxygen? I'm going to go up to my equation and I'm going to box the unknown. Don't take shortcuts with this. You really do need to box the known and the unknown. If you don't, you're very likely to grab the wrong coefficient. So now I'm going to start back to the problem. So here's my known, 9.5 grams of sodium. Now I'm going to need to, it's how many grams of sodium in 1 mole of sodium. So I'm going to need to look at my periodic table. So I'm going to look at that, look up the weight of sodium, and it's 22.99 grams per 1 mole of sodium. You're just going to read that right off the periodic table. Now I'm ready for I'm going to turn this into what looks more like our usual. This is our usual table. So now I'm ready for my bridge, to go from my known to my unknown. So if I have moles of sodium on the top, I'm going to need moles of sodium on the bottom. So this number here is going to come right into this box. And I'm ready for my bridge. I'm going to go to my unknown. Well, there's 1 mole of oxygen per 4 moles of sodium. Now my answer is asking just for moles of oxygen. So actually I'm done with this problem. I'm going to put that in the calculator to solve it. So when I put that in the calculator and then round to the right number of significant figures, which is 2, I'm going to get 0.10, 2 significant figures, moles of O2. So now I'm going to go ahead and I'm just going to erase this one part so that I can mark my knowns and unknowns all right. And here we go. So I'm going to look at this question and I'm going to pull out my knowns. I've got 12.5 grams of sodium oxide, and that's my known. So I'm going to also go ahead and erase things from here just so that I can box what I need. So my known is the sodium oxide. Well, I'm going to look at this. I've got sodium. I've got oxygen. This one must be sodium oxide. So there's my known. Now I'm going to go ahead and do my unknown. How many grams of sodium? So I'm going to box this is now my unknown. The first part of me is done for me. Okay, 25 grams of Na2O. This is the molar mass of Na2O per 1 mole of Na2O. And now I'm going to need my bridge to go from Na2O to sodium, Na. So this is going to come into this box right here so that my units match off. So 2 moles of Na2O. Now I'm ready for my bridge. So this one's going to come down and it's going to go right on the top to 4 moles of sodium, Na. So the next step is to look up. We've got 1 mole of sodium and I need to find out how much that weighs. And I've already looked that up. It's in the next problem. So 22.99. And again, I'm getting that from the periodic table. And now I'm ready to calculate. So I put in fraction button, 12.5 times 4 times 22.99. Come down the bottom of my fraction. 62.0 times 2 times 1 equals, and then I need my SD button, and that's going to give me, and I need 3 significant figures, so my answer is going to be 9.27 grams of sodium. And that's how I do that problem. Let's look at another one. This one I'm going to annotate a little bit less. So it says acetylene gas, and it tells me the formula C2H2 undergoes combustion to form carbon dioxide and water when it's used in an oxyacetylene torch for welding. Balance the reaction and answer the following questions. So I'm going to go ahead and balance this. So I've got carbon, I have hydrogen. Oops, I'm going to make that a little bit bigger. So I've got carbon, hydrogen, and oxygen. I'm going to do my count. I have 2 carbon on this side, 2 oxygen on this side. Sorry, 2 hydrogen and 2 oxygen. On the product side, I've got 1 carbon, 3 oxygen, because I've got 2 in the carbon dioxide and 1 with the water. And then my water, I've got 2 hydrogen. There we go. So I'm not balanced. So I need to have 2 carbons. The only way to get 2 carbons is to put a 2 in front of here. Now I'm going to update my totals. And that gives me 4 oxygen plus the 1 in the water. And that's going to give me a total of 5. I'm balanced for carbon. I'm balanced for hydrogen. I'm not balanced for oxygen. So 5 and 2, the lowest common denominator is going to be 10. So in order for me to get 10 of the oxygen, I'm going to need to put, I've got 4 here with the carbon dioxide. I want to have 6 more, so if I put 6 here, let's see what it happens. So now if I'm updating my total, I now have 12, 6 times 2, hydrogen. I've got 6 water plus, 6 oxygen plus 4 oxygen. That's going to give me 10 total oxygen on that side. Now I'm going to bounce across to the other side. I've got 12 hydrogen. I want 12 here, so if I put a 6 in front of this one, update my total. 6 times 2 is 12. 6 times 2 is 12, so I'm going to update that. Now I'm going to bounce back across to my carbon because I'm still not balanced. In order to have 12 carbon, I'm going to need a 12 in front of this. And update my total. So I've got 12. Now I've just changed my oxygen number. So 12 times 2 is 24, plus the 6 over with the water. That's going to give me a total of 30 oxygen. So now I'm balanced for carbon. I'm balanced for hydrogen. I still have to do the oxygen. I need 30 on the reactant side. So what I'm going to put in front of this is 15. 15 times 2 is 30. So now that's balanced. So my coefficients, just to make this a little bit neater, let me go ahead and just make this all look a little bit better. So that's going to be a 12. And I'm going to take a look at this and see if I could reduce my coefficients, because it's possible that I might have gone too high. So I'm going to look at all my numbers. And I'm going to say to myself, I've got 6, 15, 12, and 6. Well, I can divide every single one of those by 3. If I divide 6 by 3, I'm going to get 2. If I divide 15 by 3, I'm going to get 5. If 12 by 3 is going to be 4. And 6 by 3 is going to be 2. So what I'm going to do is those are the final coefficients that I should have. I want to make sure that I've got coefficients that are reduced. So when we did our initial tally on this, we went higher than we should have, and that's okay. So this is going to be 2, 5, 4, and 2. Now I'm just going to erase the ones that are up top. There we go. So now I've got my balanced reaction, and I'm ready to do my problem. So it says how many grams of water can form if 113 grams of acetylene is burned. There's my known. Now I've got to look for acetylene. Now it did tell me what the formula is. I've got 2 as a coefficient, so I'm going to need that one. Now I'm ready for my unknown, grams of water. I'm going to box that coefficient. We got 2 for that. Now I'm ready to start my problem. 113 grams of C2H2. Starting with grams, so I'm going to need to calculate the molar mass. So I've got 2 carbon atoms. Each one weighs 12.01. I've got 2 hydrogen atoms. Each one weighs 1.01. Going to multiply those, which is going to give me 24.02. Multiply 2 times 1.01, you're going to get 2.01. Add that all up, and we've got 3062. So a mole of C2H2 is going to weigh 26.03 grams per 1 mole. So I need grams on the bottom of C2H2, and that's going to be 26.03 grams per 1 mole of C2H2. So now I've just done my molar mass. If I'm comparing my steps here, it's looking like this problem right here. I'm ready for my next conversion factor. I'm ready for my mole bridge. So I'm going to go here, and my known is 2 moles of C2H2. My unknown is 2 moles of H2O. And now I'm ready for my last conversion factor. I want grams of water, so I need to do one more conversion factor. I've got mole of water on the top. 1 mole of water weighs how many grams? Got to grab my periodic table. To calculate this one, we've got hydrogen, and we have 2 of them. Each of them is 1.01. And we've got water, and we have 1 of those. Oxygen, and we have 1 of those, and that's 16.00. Multiply this together, and you're going to get 2.02. We've got 16 times 1, which is 16.00. Add them together, 2, 0, 8, 1. It's going to give you 18.02 grams per 1 mole of water. 18.02. Now I'm ready for the calculator. And we do that in the calculator, you're going to get 78.2, because you need 3 significant figures, grams of H2O. And there you have it. I'm going to do this one last problem, and then I'm going to call it quits for tonight. So the question is, how many grams of acetylene react if we have 1.1 moles of CO2 produced? That's my known. My unknown is the grams of acetylene. So up here for my coefficients, again, I'm going to erase these so I can start fresh. Except for I just erased what needed to be balanced. Let me write those back in there. We had 2. We had 5. We had 4. And we had 2. And those were the coefficients that we had that I shouldn't have erased. So the ones I'm going to need for this problem is I'm going to need CO2, so I'm going to box that. I'm also going to need acetylene. Now I'm ready to do the problem. So my known is 1.10 moles of CO2. Now I'm starting at moles, so I'm going to make sure my units cancel out. So if I have moles of CO2, I can just go to my mole bridge. I don't need to have the gram part. So I've got 4 moles of CO2 per 2 moles of water. Oh, sorry, it says acetylene is my unknown. Let me back up. C2H2. Now I'm ready. I'm looking for grams, so I have to have one more conversion factor. 1 mole of C2H2, and I've already calculated that, is 26.03 grams. And now I'm ready for my calculator. So you can see if I start at moles, I'm actually going to save myself a step. But the question is what will tell you whether you can start with moles or not. Times 26.03, drop down to the bottom, 4 times 1 equals. So I'm going to get 14.3 grams of C2H2. And that's my answer. Okay, that was a little bit about stoichiometry.